Moving along in our module 5, which is looking at our transformations. Here, this particular video is getting into the Fourier transform. Haha. So I love the Fourier transform. It's like the bread and butter of what I do. So, but do I do the math on it every day? Certainly not. So I am going to introduce it to you guys because it is something used all the time in remote sensing, and it is a very powerful tool for remote sensing. So, and it's used everywhere. And it is like probably the most commonly used transform across the board in like every industry. So I need you guys to know what it is. I don't expect you guys to be able to derive it. I don't expect you guys to be able to like create functions and everything else. I'm not expecting that. I'm just going to give you a breakdown of a very simple scratch in the surface type of breakdown of what the Fourier analysis looks like and kind of why it relates to remote sensing. So the Fourier transform itself, it actually was developed by a French mathematician back in 1768. Yes, it is old, but it is still very relevant. And he developed this theory and a big, long thesis that was titled The Analytic Theory of Heat. And so, thinking back to what I was talking about, all the way back to the different light theories, he's looking at heat. So he's looking at Planck's theories, and I don't remember what exactly the order all of this came in, so I'm not a history person, but really he's trying to figure out heat. And what does some of the remote sensing area look at? Well, heat, right? So this really falls into that. So his theory was that every function can be broken up and reconstructed without information loss. So he's like, well, why not? Why can't we just like take a wave, for example, and we can see one made up here, and take that wave and we're going to break it up into the small pieces that help represent it. So over here we have our little waves, and then it like gets a little bit bigger, and then it gets even bigger, and then it gets really big. So that is what this is representing here, is that if we were to take all of these and put them all together in terms of like constructive and destructive interference, we would actually develop this wave over here. So he says that, and this should be spatial, spatial domain, not the special domain. What he says here is that, hey, we can, just like visible light, if you take a prism and you shine light through it, it's going to spread out. You're going to see all the different wavelengths that come out of that and make that rainbow, right? So what he says is you can definitely do that with any function. So so it takes this in time or space, and then it converts it into the frequency domain. So we're looking at all these different frequencies. So there's two components to the Fourier analysis. One of them is the Fourier series, which is kind of the first one that everyone tends to learn. And so the idea behind the Fourier series is that every function that repeats itself can be identified as the sum of the sines and or cosines of different frequencies, each multiplied by a different coefficient. Linear function, basically, right? Except you have sine and cosines. The rule about it is that it must be periodic, which means that it repeats, and that there's some basic math rules but I'm not going to get into them here. So the Fourier series becomes a sum. So we have all these addition signs, we have sines and cosines, we have coefficients, and we add them all together. So relatively simple idea, and as you go further away from the first coefficient, it becomes smaller and smaller and smaller of a component. So, but the idea is that it's like this infinite series breaking down every function, repeatable function, into these parts. So, but then we have the issue of, well, what happens if it's not periodic and it doesn't necessarily repeat itself totally? This is where the Fourier transform comes in. So any function can be expressed as an integral of sines and cosines multiplied by a weight. So all we're doing is taking integrals. This, it doesn't require them to be periodic. Okay, so that's not a rule. And with the Fourier transform, it has to have a finite area under the curve. So as we know, an integral is the calculation is finding that area under the curve. If it's infinite, then this doesn't work. But the Fourier transform does require the function to be continuous. It cannot be a discrete function. So it does require that. So as we moved forward with the Fourier transform, it was used quite a bit. It required a lot of mathematical equation and calculation. But as technology improved, we ended up now with computers. So the computers were able to like speed up the process, and that was called now it's called the fast Fourier transform, FFT. Now you're also going to see forward Fourier transforms, and that's also represented as FFT, depends on the software you're using. But the fast Fourier transform was a faster way of applying the transform equations and the breaking up of the function expression. Computers were able to do it faster than humans. So the efficiency of using it has greatly increased, and now we have a great way to interpret this as well, because now we can apply this to much bigger functions and get some interpretation value from it. So that's great, that's fun. What does this mean? Well, here we go. Here's a Fourier. So if we take a picture, these are just like obviously high oblique photos. But if we take a picture and we change this picture into a Fourier transform, this is what it looks like. So we have high frequencies and low frequencies that kind of go around an axis. This axis is defined by the straight lines that you're seeing within the actual photo itself. That's why this one below, if you see this, notice that there's not many straight lines like what we have in here. So you can see that it kind of disappears, the vertical and horizontal. It's much more defined here. Then we can check out the phase of this. So we take amplitude. So this is what this is. And then we take the amplitude of my Fourier transform, which is the full value. And then we're going to look at the phase of those values as well from the Fourier transform. And then we're going to apply some sort of filter, and then we spit it out. So the idea behind the Fourier transform is that we're not losing any information, and that this would appear to be very, oh my goodness, you have a very different image compared to this and looks much messier. If we are to add these together in one way or another, we could end up with the inverse looking like that. And if you apply some filtering and everything to it, then it's not too bad. Although this one is showing, I see what they've done here. So in this particular example, because this is from a reference, they've actually taken the frequencies of Istanbul, so this image, and they've incorporated them with Kotar. So the same frequency, two totally different images are put together. So that is another reason why we would do Fourier transform, is that we're trying to take two images and we're trying to put them together into one. Now this is a little bit more, a little bit harder, I guess, but you can see the mountain there. You can see the hill that's been put in there. And we got the hill, and then we got the buildings in this one. So kind of neat, hey? So you can kind of put them together. They don't always look like this quality, but I wanted to bring this particular image in so you could see what a Fourier transform looks like in terms of the image. Take a photo, got these lines that come through that tell us what's vertical and what's horizontal, and then we can put it into a phase, and then we can combine them and create something new. So the filtering in this case would be applying the different kinds of images, and we end up with a different filter. So a lot of the times we apply filters with Fourier transform, and that's what they look like. So the math. So, so this is the math that we would see for a one-dimensional Fourier transform, which is not something that we do in remote sensing, but it does give you the basic start to it. So we have the spatial domain and we have the frequency domain. So the frequency domain is referred to as this capital F at U. So yes, F at U is the frequency domain, and then the lowercase f with an x is the spatial domain. So in order for us to go forward, which is going into the Fourier transform and moving into the frequency domain, we would find our function of our graph, and then we multiply it by this, and we're taking the derivative, or not the derivative, the integral of it, right? We were talking about taking the integral. So f at u is the integral of f at x times e to the exponent of negative j 2 pi ux dx. So u is the frequency, x is the spatial information, j is the imaginary number of the square root of negative 1. So yes, we get to deal with imaginary numbers in the Fourier transform. I am very aware that you guys don't do imaginary numbers in math, so this is why we're not doing this in numbers. We're just looking at the equations. So they're pretty straightforward. So again, if we want to reverse it, f at x is the integral of capital F at u times by e to the j 2 pi ux and then du. Again, noting that really the only difference is the inverse of e. So if we want to go two-dimensional, now we just added more variables. We have f at u and v. We do a double integral for f at x, y, and then we have our e and then dx, dy. And then we reverse it, going back to the spatial domain. Here we go. Very much the same thing. As complicated as it seems to sound, the hardest part is the integral. It just means that you have to do partial integrals based on each individual variable. Then we have the discrete Fourier transform. Now, this is really going more into remote sensing. So the discrete Fourier transform is because we have a number of pixels. Pixels are actually like discrete. Now you're going to say, well, before your rule said that it has to be continuous. Well, it is continuous in terms of the energy, and it is continuous in terms of the image itself. What it's not continuous in is the fact that it's a pixel. So we can use discrete Fourier transform. And so we'll use f at u and then 1 over m, which is the number of pixels, and it goes through every pixel, looking at the function of each pixel, multiplied by e to the exponent of negative j. And then to reverse it, the f at x comes out, and we inverse m and go from there, right? So very much the same as before, we just have this that we have to worry about, and it's a sum instead. So, but this is the starting point of, okay, this is actually really easy to work with because now we're just dealing with sums and we're adding up all of that. But these e's are kind of a pain, right? So how can we deal with this natural exponential? And that is through Euler's formula. That's EU is actually pronounced E, like oi, in German anyways. So maybe I'm wrong in any other language, but that's what it's pronounced, Euler. So Euler's formula says we can put everything onto a graph of real numbers and imaginary numbers. And so these real numbers, the real numbers is going to be on the x-axis, the imaginary numbers are going to be on the y-axis, and we can split it up into polar coordinates. So here we have e to the j theta. So my angle is actually, in this case, is going to come from the real numbers. So we're working backwards from geographic coordinates. But my angle is here. So I take cos of the angle plus the j sine of the angle. And that gives me my location. Now, j is still an imaginary number, but even if we were to hold that and just say, we'll just put it in front of this component all the time, the math is really straightforward. So it replaces this e to the j theta, and theta is the function of whatever is there. So if we come down here and look at the discrete formula, we have f at u equals 1 over m, and then the sum of f at x, And now the E function that we saw before, right here, changes to be cos of that, that exponent minus j sine of that exponent. It looks longer, but not as intimidating. A little bit easier to do mathematics with, and that's where we move into calculating the actual value of f at u and then the conversion of f at x. So this is where polar coordinates come in. So especially in microwave remote sensing, we separate it up into these three components for polar. The first one is magnitude, so that's also my intensity. And so you can see that this is just the real and the imaginary, and it's the radius, right? So if you were to say r theta, it's the radius on the imaginary and real coordinate system, and we get an absolute value of it. So again, then we multiply by e to the negative j theta u, and that gives us my magnitude. And it's also known as a spectrum, but it gives me the magnitude of my wavelength. Then I have my phase, so here's my phase, and that's psi u equals the tan negative 1 iu over ru. So I is imaginary, r is the real, and again, it's just an angle that we're taking. So now I get my phase, and I can find out my phase for every point and every pixel on that graph. And then I can figure out my amplitude or power. So that's p at u is equal to f at u, the absolute value, squared. Or we could just, it's really just this formula here, the Euclidean distance, and without the square root. So that's Fourier transform. The next objective is transform an image from spatial domain into the frequency domain. You will do this in your assignments, so we'll spend some time doing that. But here's just giving you an example. So here is Goofy, and we're going to apply him to the frequency domain. So you can see that it's kind of all over the place. There's no real like set lines, and then what you could do is add a color table. It's the color table that makes it look all bright and fancy colors. Otherwise, it's just black and white like this. If we blur him, this is what happens, right? So again, we have a little bit more of it's kind of chaos everywhere else, but we can kind of make out like that there's a vertical shape, and it's probably because of his ears and the eyes and the teeth, and it's just like longer this way anyways, but you can really see it here because the background is just kind of fuzzy. You can see how that impacts it. Same with over here, we have a brick wall. Check that out. You can see vertical lines and we see horizontal lines, and there's intersections along those lines, and that's very clear. Here's cubes, lots of lines happening there. Look at the frequency on that. Lots of fun. So some of these make some pretty psychedelic images. So just be aware of that when you're taking a look at it and seeing it. I do suggest, and actually I want you to apply a color table to them so that you have some pretty like psychedelic looking pictures, and you can put it up and be like, there's Calgary. Or you could put it up and be like, there's Hawaii, or wherever you're working in the world. There's Vegas. Check that out. and it becomes a conversation piece. So all it is just going into Envy and typing in, you can say FFT. You click it, you put in your image, and bang, it's done. It's as easy as that. So really straightforward to do in software. So the Fourier transform, again, we use it for filtering. In microwaves is a little bit different because we use it for analysis because we work with like the amplitudes and phases and such. But for visible light, we use it for filtering to either sharpen or to smooth, all kinds of different reasons to use it. So that's the Fourier transform. It's not as scary as everyone tries to make it sound. The math can look pretty intimidating once you start adding in functions, but really the mathematical function comes from whatever you're doing. So that's where that comes from. So there's Fourier transform. There's one more analysis, and then there's a bonus objective after this.